This presentation will describe one strategy for developing a global fit analysis pipeline for LISA, and give a brief status update for how that development is proceeding. The figure on the left shows the power spectra for different source types in the LISA measurement band to give a sense of how rich the data are. The LISA data stream will contain a large and unknown number of sources. Many of the sources will be overlapping one another in time and frequency. While most individual overlaps between pairs of sources are small, the large number of sources means that the many small overlaps accumulate and cannot be ignored in the analysis. So the need for a global fit analysis which simultaneously analyzes all source types is clear. Doing so avoids source confusion, although that is a lesser problem so long as some care is taken into how the analysis is deployed, thanks to the small overlaps between different source types. The more important mitigation from the global fit is to fully marginalize over all model uncertainties. The clear disadvantage of the global fit is that it is complicated, but I will explain today that it is a logistical challenge of developing a global fit algorithm, not a problem for designing the algorithm from a theoretical standpoint. The underlying engine of the global fit pipeline I'll describe here is the Markov chain Monte Carlo, or MCMC algorithm. First, a brief MCMC primer. We start with some predictive model for the data M. This includes our model for the gravitational wave signals, but also our model for the detector response to those signals and the detector noise. The model is described by some large number of parameters x, and using Bayes' theorem, the probability density for those parameters given some data d is shown here as the product of the likelihood and the prior normalized by the marginalized likelihood. The MCMC algorithm produces a set of independent samples from the posterior, and from those samples we characterize the posterior, for example by computing different moments or correlations of the distribution. The reason the MCMC algorithm is so valuable for sampling from the distribution function is that it is well suited to large parameter spaces. The MCMC algorithm formally always converges, though the time that it takes strongly depends on the design of the sampling algorithm. However, it is generically faster than brute force computation of the posterior on some grid when parameter space gets large, and the LISA data definitely fits that bill. The MCMC results can also be used as a one-stop shop for source detection, characterization, and quantifying confidence in a detection candidate. Now you might say that what I've described here is any stochastic sampling algorithms. There are a large number of algorithms that can do this. So what is so special about the MCMC? The reason we focus on MCMC is that there is a straightforward way of also sampling over different models, which is critical for LISA when there is such large uncertainty in the number of detectable sources in the first place. With other fixed dimension sampling algorithms, we suspect it would be impractical to sufficiently cover the model space, although there may be some clever transdimensional algorithms out there that we just haven't yet heard of. So we're focusing on MCMC. But wait, you might protest. The parameter space is large, MCMCs are slow. How could you ever possibly cover that large of a parameter space with a sampler? And our answer there is to use the blocked Gibbs sampling technique, where only a subset of the parameters are updated in each step of the chain. So what is blocked Gibbs sampling? Imagine two blocks of parameters A and B, here compressed onto a 2D plane, but A and B can both represent several individual parameters. The Gibbs sampling approach is to hold one block fixed, say A, and then sample over block B, then hold B fixed and sample over A, and rinse and repeat until the full posterior is covered. As suggested by this little cartoon here, the blocked Gibbs approach has a pretty horrible convergence when the blocks are highly correlated, but we already discussed how the actual correlations between sources are generally small. What we really need the global fit for is to account for the uncertainties in each block. This strategy allows the individual blocks to be developed independently with an agreed upon protocol for sharing data between the blocks. It also lends itself to being broadly parallelized and thus taking advantage of the distributed computing model currently favored by the LDPG. Another advantage is that this modular design allows the blocks to be added or removed from the analysis chain without disrupting other parts of the analysis, making the global fit algorithm adaptable even on the fly. This flowchart for a proposed global fit pipeline with independent blocks for parts of the model of gravitational wave sources, detector noise, and data calibration. The green canisters are the data shared between the blocks, updating the subset of the model parameters. Exactly how to best share information between blocks is still to be determined, but as a starting point, we imagine exchanging residuals and the noise covariance matrix from one segment of the analysis to the next. The algorithm then cycles through many updates from each block and collects samples to then be formatted as the higher level data products. You can get an update on the progress of developing a few of these blocks during this meeting. Jessica Page has a pre-recorded talk about forming the TDI channels themselves as part of the global fit. And Kristen Lakios is presenting a live talk on results from our analysis of the LISA data challenge Radler dataset containing the galactic binaries. Neil Cornish and Kevin Schumann also recently published a paper describing a supermassive black hole analysis based on Markov chain Monte Carlo techniques, which was designed with the intent of sharing information with our current UCB pipeline in the not too distant future. So you are now adequately convinced the Gibbs sampling sounds like a good way to go. What are we currently working on right now? So one thing to be wary of is the computational cost of this global analysis, particularly in the context of continuous sources, as the amount of observation time starts to be measured in years instead of months. Reanalyzing the full LISA dataset each time we want to update the detection catalogs will become increasingly burdensome. So how do we efficiently update our models when new data are acquired? So if we start with the first segment of data, say D1, the posterior is the same as we had written before. And now we add a new block of data, D2, and the joint posterior takes the form shown here. Because D1 and D2 are independent observations, joint probabilities are just the product of the individual terms, so it can be broken up into its pieces as shown here. And here we can see that the ingredients of the posterior on D1 appear in the joint posterior for D1 and D2. That means we can rewrite this joint posterior as shown on the bottom, where now the role of the prior in the analysis of the data containing D2 is played by the posterior from the analysis of D1. In other words, we are using yesterday's posteriors as today's priors to avoid having to reanalyze the data. Now, this idea is not new, but it is seldom taken advantage of because the output of a Markov chain Monte Carlo is a set of discrete samples, an example shown here for a simulated galactic binary source, but the prior needs to be evaluated anywhere in parameter space. So we have to take this set of discrete samples in this large dimensional parameter space and turn that into a continuous function. So to do that, we are experimenting with approximating the posterior using Gaussian mixture models, and then we use that Gaussian mixture model of the posterior as a prior to analyze new data. Shown here in purple are the marginalized posteriors constructed from this Gaussian mixture model. The 1D posteriors are the sum of all of the individual Gaussians in the model, and the 2D posteriors show the 2 sigma contours of the individual Gaussians that go into the fit. And so we can post-process our analysis to develop this Gaussian mixture model, and then when new data are acquired, analyze it using this posterior now as a prior and not having to reanalyze that already visited data. So here's a demonstration of using this Gaussian mixture model prior on a simulated high-frequency galactic binary. In each of these panels, there are 2 overlaid posterior distributions taken from the galactic binary Markov chain Monte Carlo code. The blue distributions are coming from analyzing the full data from the beginning of observations until the end, using our usual naive priors about what the source parameters can take. The magenta curves are analyzing the data in 6-month intervals, only analyzing the latest 6 months worth of data and just using the posteriors from the last analysis as priors for the current one. The left-hand panel is for a 1-year observation. The right-hand panel is for a 2-year observation. And the takeaway point here is that these distributions are pleasantly indistinguishable from one another. Not only do we get effectively the same answer by using the priors versus analyzing the whole data set, but the computational savings for using these priors are fairly dramatic. So the figure on the right-hand side there shows the cumulative cost of the analysis if our goal is to update the source catalog every 6 months. The colors are the same as before, so the blue curve there is if we're analyzing all of the data from the start of observations until the day we want to update the catalog. And the magenta curve is if we are only analyzing the data in 6-month intervals using yesterday's posteriors as today's priors. After 2 years worth of observing, the difference in cost is fairly dramatic. So using the Gaussian mixture model prior is about 20% the cost of doing the full analysis. And as you can tell by the shape of that blind search curve, this is going to get worse as more and more data need to be analyzed. And so as we get deeper and deeper into the mission, using these priors becomes a bigger and bigger savings. Now, this is hot off the presses. We've only really tried this out on a few particular galactic binary sources. Plenty more testing needs to be done to understand in which parts of parameter space we're not suffering any biases from using these priors, and also start to explore how this method works for other source types as well. But at the very minimum, this is a really promising and encouraging sign, and we'll keep poking at this to see how it goes. So that brings us to the end of our update on our progress towards a global fit pipeline. Hopefully by now you are convinced that this is a solvable problem, and continue watching this space and others as we continue to get closer to a solution. Thank you.